Hello, Computer Science 221 students. Welcome to the lesson about Introduction to Graph Theory.
Alright, as a warm-up question, please consider this relation. Define a relation T on the set A to be 2, 3, 4, 5, 6, 7, 8. Uh, Let me write a few of the order pairs that belong to the T. For example, 2, comma 2 is in T. The reason is, think about this everyone. If you choose x coordinate to be 2 and then the y coordinate to be 2, 2 minus 2 is 0. Do you agree? So 3 divides 0 is a true statement. Therefore, this order pair is in the set T. Similarly, 3 comma 3 is in T and so on. Do you agree? Um, the only difference between today's lesson and compared to the previous lesson on relation, I would like to write down something new, which is treat each element in the set as a vertex of a graph. Look at this. So we have a vertex like this: 2, 3, 4, 5, 6, 7, 8. We have vertices placed like this. Now, 2 comma 2 means everyone. It means 2 maps to 2, 3 sends to 3. That's kind of how we should treat it, okay? Now, 2 maps to 2 means what, everyone? It means 2 goes to 2 itself, which is a loop. Clearly, everyone, 3 comma 3 is in T. That means 3 goes 3 itself. So it's a loop. Okay, now consider other order pairs like this: 2, 5. Clearly, 2 minus 5 is divisible by 3, right? So what that means is that 2 comma 5 is in T, okay? That means we have an edge comes from 2 going to 5, like so. But it's vice versa, do you agree? 5 minus 2 is also divisible by 3, so we have a edge directed like this. 5 goes to 2. Do you get the point? Now, 3 take away 6 is also divisible by 3, and 6 take away 3 also divisible by 3. So we have this kind of edge. Continue the process, we get the following. I know this looks ugly. I'm not a good artist, but this is a graph. Trust me. This kind of graph is called the directed graph. Everyone, before we move on to the next slide, let's learn new vocabularies. The new vocabularies first I want to tell you are called vertices. You see, we have V1, V2, V3, V4, V5, V6, V7. We have 7 vertices. So the vertex set is. Now, did you guys notice that we have a line segments joining vertices? The line segments joining vertices are called edges. So look at this. We call E1 representing edge number 1 because it's joining the two vertices V1 and V4. So it is one of the edges. So how many edges are there here? We have E1 here, E2, E3, E4, and then E5, which is a loop, and then E6. So we can write a set of edges like this. Do you remember table of values? Table of values looks like this, right? Something like this. This time, I want to tell you new vocabulary, which is called edge endpoint function. For example, if I write edge over here and endpoints over here, the first edge E1 is connecting V1 and V4. So you just write it like that. E2, look at this. E2 is connecting V2 and V3. Okay, this is the end of writing edge endpoint function. So I hope you understand this one because if you understand one of them, you probably can understand the rest easily. Next, we call E2, E3 as parallel edges. The reason is they have the same endpoints like so. You see, E2 and E3, they are parallel, connecting V2 and V3 vertices. The vertex without edge is isolated. So this is called isolated vertex. And I think you understand this one. If you have this kind of structure, it's called loop. This E5 is the edge connects a vertex V4 here to itself. That's why it is called a loop. Okay, please remember these new vocabularies with edge endpoint functions, vertex edge sets, and so on. Okay, here's the proper definition of graph G. This G consists of two finite sets. We already talked about those two finite sets, which is the vertex set and the set of edges. The vertex set is called V of G. The set of edges is called E of G. So here are the new vocabularies. Two vertices that are connected by an edge are called adjacent. This is another vocabulary as well. Two edges incident on, you can look at what incident means right above there. Two edges incident on the same endpoint are called adjacent as well. And finally, we already know a vertex on which no edges are incident is called isolated. Okay, let's quickly try an example. Suppose this is the graph G. Write the vertex set, edge set, and the edge endpoint function table. Vertex and edge sets are easy to do because you just have to copy down the VIs and EJs. So let's write it down. We currently have 6 vertices from V1 to V6, and then we have 7 edges, E1, 2, E7 over here. We just have to write it down edge endpoint function, which is a kind of table of values. Okay, everyone, I'm running out of space, so I was a little bit struggling. So I hope you take time and look at this and see if my work is correct or not, because it's pretty straightforward. Part B, find all edges that are incident on V1. All you have to do is just check surrounding edges near V1, which are E1, E2, and E3. That's the answer. Okay, next, find all vertices that are adjacent to E1. I think there is a typo. It must be find all edges that are adjacent to E1. So find all edges that are adjacent to E1. It's actually, by the definition, two edges incident on the same endpoint are called adjacent. So E1 is adjacent to E2, E3 because it's sharing the same vertex here. Because E1 is connected to V2 as well, the edge sharing V2 is E4. So altogether, the answer for the first part of part C is E2, E3, and E4. Next, we have to find out all the loops. All the loops are E6 here and E7 here. The reason is, everyone, because these are the edges which connects a vertex to itself. So E6 and E7 are the answers for this guy. Finally, all parallel edges. Well, I see this guy is parallel edges. Okay, everyone, that's the end of the first example. I hope these new vocabulary is getting easier to understand. Next example is to draw more than one picture for a given graph here. We have V1 up to V4 as a vertex set, E1 up to E4 as edge set, and we have edge endpoint function given as follows. You know, I think the simplest way to sketch more than one picture for a graph is to rearrange the vertices. That's all. For example, let's say I have one vertex form looks like this. Okay, and then follow this edge endpoint function. For E1, connects V1 to V3 or V1 and V3. So next, E2 connects V2 and V4. Next, E3 connects V2 and V4 as well, so they are parallel. Finally, E4 is a loop because we only have a singleton set here. V3 is the only lonely guy here. This is one of the choice. And another choice is that you can rearrange the vertices like so. And then follow the edge and endpoint function. E1 connects V1 and V3. And then we have parallel edges for between V2 and V4. And finally, we have a loop at V3. Congratulations, these are the two pictures for a graph, G over here. The final thing that I would like to discuss with you for this first part of the video, I want to mention something about directed graph. Actually, do you remember at the very beginning of today's lesson, we discussed about this one, which is an example of directed graph. So in a way, you already know what's going on. So the only thing that I have to tell you is that when you're talking about directed graph, V of G stays the same, but we have to use D instead of E for directed edges. It's just new vocabulary again. Now we use an edge associated with a pair VW of vertices written this way in order pair. You know what? V first and W is the image. So we have to go from V to W. Do you understand? So look at this, everyone. A to B, there's an edge 1. A to C, edge 2, and so on. So if you understand this process, please sketch the relation with the graph. This one is much easier than the warm-up question at the beginning. Okay? All right, everyone, have fun. And I'll come back with part 2. See you soon. Part number 2, special graphs. I'd like to start this second part of the lesson with the definition of simple graph. A simple graph is a graph that does not have any loops or parallel edges. We denote an edge E to be this set. Okay, so let's start with drawing some simple graphs, given that we have 4 vertices, U, V, W, X, and 2 edges. And here's important word here, 2 edges. We need 2 edges only. One of which has to be U comma V. In other words, there is an edge connecting U and V. Let's sketch the 4 vertices here. Let's say we have these 4 vertices. They say draw all simple graphs. That means this is one of many, I guess. So one of the choices that I can think of is maybe connect. We must connect U and V together. That's for sure because that's what the question says. And they said we need to have 2 edges. In other words, we need to have either this way or this way or this way and so on. So here you go. This is choice 1. And another simple graph drawing given this constraint is this. Maybe this time we can connect, instead of to W, we can connect U and X together. Of course, everyone, this is a simple graph. That means we should not have any loops or parallel edges. So far these 2 graphs are fine. This time, let's connect V and W together. And the fourth one is when we connect V and X together. The next simple graph that we can work out is Of course, we have to connect U and V, but the only other combination we can have is this joining W and X. Okay, so these are the possibilities for simple graphs given these conditions. Okay, that's the end of the warm-up question. Here's the new definition. Complete graph. It's actually a very simple definition, everyone. If you understand the definition of simple graph, which we just did it in the previous slide, then this is actually pretty straightforward. This assumes that we have a simple graph with n vertices. And the only important part that you have to remember is that we have exactly one edge connecting each pair of the vertices. That's the main keyword for this definition. For example, everyone, when we say K1, right, that means we only have one vertex. Then we don't have to worry about the edge. For example, it looks like this. K1 means only one vertex. That's it. That's a complete graph with one vertex. Now, let's suppose we have more than one vertices. Let's say K2. K2 means we have two vertices. Let's say V1 and V2, and connect them together. Because by the definition of the complete graph, they say we have to have exactly one edge connecting each pair or one pair of the vertices here. K3. We must have an edge connecting each pair. So let's denote this to be V1, like so. Then it must look like this. So this is a complete graph for K3. K4. The complete graph K4 looks like this. This seems obvious, right, so far? But also, please do not forget about something. Because they said we need to have exactly one pair of each pair of distinct vertices, we must connect V2 and V4, and then V1 and V3 as well. So this is K4. K5. Suppose our vertices written this way, we need to join every pair by an edge. Okay, this is obvious, right? Now let's connect V1 and V3 together. Okay, that's also obvious so far. Now we need to connect V2 and V4. At the same time, we need to connect V2 and V5. And finally, V1 and V4. So it looks like this. That's the complete graph for K5, and you can continue and so on and so on. Okay, let's move on to the next definition. Bipartite graphs. Let's consider a simple graph G looks like this in number 1. As you can see, we have 6 elements in the vertex set. We have a vertex set with 6 elements. The idea is that we're going to partition this vertex set into 2 different vertex sets, subsets like V1 and V2. And here's the important part, everyone. Listen carefully. Elements in V1 may be connected to elements in V2. Okay, that's okay. That's allowed. However, elements in V1 cannot be connected to themselves. Elements in V2 also cannot be connected to other vertices in V2. That's not allowed. As you can see, V1 is not connected to V3, V3 not connected to V5, V1 not connected to V5. They're not connected to each other in this disjoint set here. That's the only thing that you have to remember for bipartite graph. So the idea is as long as we can transform a simple graph G into looks like this, then we can call it a bipartite graph. Now, the next definition that I would like to mention is something called complete bipartite graph. Please pause the video and take a minute to read this whole sentences here, and then I will explain carefully what this complete bipartite graph means. Okay, now assuming you have read the definition, even if it looks confusing and not really understandable at the moment, let me explain it to you carefully. To do this, let's go back to the previous slide. When we talk about bipartite graph, did you notice that we have two disjoint sets? Like in this case, is we have three number of VIs, and then we have three number of elements in the other set. KMN, okay? This M is actually counting the number of elements in the first set. N is counting the number of elements in the other side of the set. So let me draw K32, for example. And we are already assuming it's a bipartite graph. So we have vertices, three vertices on the left and then two vertices on the right. Let's read this sentence here. There is an edge from each vertex Vi to each vertex Wj. What does it mean, everyone? It means we must have an edge containing V1 and connecting V1 and W1. We must have an edge connecting V1 and W2 as well. Could you please read the second point here? There is no edge from any vertex in the first set to any vertex in the same set. That's not allowed. So you cannot connect V1 and V2 together or V1 and V3 together and so on. Using number 1 again, we can connect V2 with W1, V2 with W2, like so. Similarly, V3 with W1 and V3 and W2, like so. But please note, W and W2 cannot be connected to each other, and then any of the VIs cannot be connected to each other. So this is called complete bipartite graph and denoted by K3, 2. Let's try one more with the K33, say. This K33 means we have three vertices on the left, three vertices on the right. And there must be an edge from each vertex Vi to Wj. Okay, I'm done with the V1. Let's try V2. Let's try V3. It is correct, but I just don't like my drawing. It looks ugly. Anyways, it's almost 2 o'clock in the morning, so I'm not gonna redo it. I hope you understand the situation. Let's move on, everyone. Before move on, this is the complete bipartite graph K33. Okay, the last definition in the second part of today's lesson is something called subgraph. Let's denote H to be a subgraph of a graph G if and only if, number 1, every vertex in H is also a vertex in G. Every edge in H is also an edge in G. Every edge in H has the same endpoints, which means vertices, as it has in G. So for example, everyone, look at this simple example. Suppose G has a vertex set V1 and V2, only two of them, which makes our life easier. And we have two edge sets, E1 and E2. So let's sketch this. E1, which is the edge 1, has endpoints V1 and V2. In other words, V1 and V2 are connected by E1. E2 is also connecting V1 and V2. So we have parallel edges, and it's not a simple graph. It doesn't matter. We're not interested in finding simple graph at the moment. We're interested in finding the subgraph of this one. Part B. List all subgraphs of the graph G. You know something? The simplest subgraph I can think of is V1. Only one of the vertex V1. Another choice is V2, right? And then another subgraph choice can be, let's say we connect V1 and V2 together with E1. Maybe actually, everyone, let's talk about this in choice 4. You know, we even though we are not connected with V1 and V2, still this can be a separate choice as a subgroup or a subgraph. So let's move on to choice 4. Now we can talk about edge. V1, V2, and it's connected by the edge number 1, but we have another edge, so it's exactly same, but we're going to use E2 for choice 5. Okay, so far we have 1, 2, 3, 4, 5 choices. I think the last choice is, the G itself. Okay, everyone, that's the end of listing out all the subgraphs of the graph G. Thank you very much. That's the end of the part 2 videos. In part 3, it's more interesting. We're going to do a little bit more mathematics, for example, addition, subtraction, multiplication, um, and, and a couple proofs, which is very straightforward. Okay, see you soon, everyone. The last topic that we're going to cover in section 10.1 is to talk about the concept of degree. For example, we're going to talk about the degree of a vertex and the degree of a graph. Let's take a look at the following. This is the proper definition of the concept of degree of a vertex and then the degree of a graph. But maybe it helps us to save some time and to understand better. We can probably look at the graph to explain things here. Stay tuned. The informal definition of degree of a vertex is, look at this. It's the number of end segments of edges that stick out of the vertex. One thing that I want to teach you is that whenever we have a loop, this loop is counted twice. So the total degree of this vertex equals 5. The reason is we have 1 contributed from there, 1 from there, 1 from there, and then 2 from the loop. So in total, we have 5 as the degree of the vertex here. Let's answer this quickly, everyone. We don't have any edges, so we don't have to worry about the V1. Let's worry about this, parallel edges with the loop. Our goal is to find out the degree of each vertices. At the same time, we're going to find the degree of this graph. We have to count the number of degrees in each vertex and add them up. That's all. Okay, degree of V1 is 0. It's because it's isolated vertex. Degree of V2 is 2 because we have 2 edges coming out of the vertex. Degree of V3 is actually 4. The reason is 1, 2, and then we have a loop. So all together we have a 4. Therefore, if we add all these numbers up, then the degree of the graph is 6. The next thing that we would like to do is to talk about the handshake theorem. This theorem actually computes the total degree of the graph G by using the number of handshakes. For example, if you look at 3 people here, and each person handshakes with other person, so each edge is the number of handshakes, like this. But if you remember, the degree of this vertex is 2, this vertex is 2, and this vertex is 2. 2 plus 2 plus 2 is 6, do you understand? So it's actually equal to 2 times by the number of handshakes. So if we treat this number of handshakes as the number of edges, then we can get the following result. It's that simple. Here's the next slide. The total degree of a graph is even. You know what? The previous handshake theorem is very useful here. Do you know why? Because we already proved that the total number of degree of G is equal to the twice number of the handshake. In other words, twice the amount of the number of edges in G. Since the number of edges is an integer, okay, the proof is completed. Maybe this is a good example for final, I don't know. By the handshake theorem, obviously the degree of G is twice the amount of the number of edges, so which is an integer. So the degree of G is even. Okay, let's try some examples using this theorem and then the previous handshake theorem. Here's the first example. Draw a graph with the specified properties or show that no such graph exists. the properties we have is we have 4 vertices of a graph with degrees 1, 1, 2, and 3. So the total graph G, 1 plus 1 plus 2 plus 3, which is 5 plus 2 is 7. This is an odd number, which means it's against what we have proved. The total degree of a graph must be even. Therefore, this is not possible by this result. Part B, a graph with 4 vertices of degrees 1, 1, 3, 3. Oh, actually, the total degree of graph is what? 6 plus 2 is 8. That means maybe we can draw some situations like this. For instance, let's have 4 vertices to be A, B, C, D, like so. A and B has degree 1. In other words, we must have only one edge coming into A. But please do not connect like this. Then it's going to be against the given condition here. Degree is going to be more than 1. So we should not draw that. Degree of B is also in the same condition as A. So like this. And then you know what? C and D both have to have a 3. In other words, each of them must have loop. So this is, I think, one of the many examples of a graph picture for this graph here. Okay, that's the end of part B. Move on to part C, please. Part C, show that a simple graph with 4 vertices of degrees 1, 1, 3, and 3 does not exist. Please take a look at the previous result. Did you notice that our graph has a loop, right? But having simple graph, then this kind of construction is also not allowed, even though the total graph of G is 8. Okay, we're gonna prove that there's no such graph exists. Maybe we can use a contradiction method, assuming that there is a graph with this condition, and then we probably find a garbage conclusion at the end. Okay, let's try. By way of contradiction, suppose there is a simple graph G with smiley face condition here. 4 vertices of degrees 1, 1, 3, and 3. Let's draw the situation. We have 4 vertices, A, B, C, D. So, I don't know. Let's just put this like that. Okay, everyone? Now, please note, it's really important. Since we're assuming that it is a simple graph G, G does not have any loops or parallel edges. Do you agree? Now, let's look at the vertices C and D. Both of them have degree 3 and 3, right? That means you have no choice but draw situation here. Then we are satisfying one condition here, 3. Actually, we also satisfy the degree of A, degree of B, which are 1 and 1 itself. Here's the problem arise. Look at the D. The D, vertex D has degree 3, but at the moment, we only have 1, right? So in order to make it 3, we must draw like this to make the D 3, you know? But here's the problem. Our assumption is that degree A and degree B should be 1 and 1. However, now we see the degree of A is 2, degree of B is 2, which is a contradiction. There must be edges connect C to ABD, right? And then D to ABC. This is a contradiction because degree of A is actually at least 2 now. Okay, everyone, that was that simple. This shows that degree of A and degree of B are at least 2, which is against what we had at the beginning. So this statement is proved. There's no such G exists. Okay, let's quickly solve one easy example here. If you read the question, is it possible in a group of 9 people for each to be friends with exactly 5 others? Whenever you're dealing with this kind of questions, on the web assign or on the final exam, please look at the group of 9 people first. And this shows the number of vertices. What this means, everyone, is that each to be friends with exactly 5 others, that means how many branches coming out of this vertex? 5, do you agree? Same for all of other, vertices. And so on, and so on. So because we have 5 branches for every vertex here, the total number of branches we have is 5 times by 9 vertices, which is 45. But do you think this is allowed or not allowed? If you said it's not allowed, then you're correct. The reason is this is an odd number. We are not allowed to have that. It's against the result 10.1.2. Okay, that's the end of the example. Here's another example that is very similar to the web assign question. Please take a moment and pause the video and read the questions. Once you're done, please continue watching the solution. If you're ready, let's do it together. This question is actually not much different than the previous question, except that there are many things. We have 3 people who are network friends with 6 other people. What does it mean, everyone? Like 1, 2, 3, and then we have 6 branches, 1, 2, 3, 4, 5, 6, and so on, and so on. So using this first piece of information, we get the portion of the total degree of a graph G, which is 3 times by 6, Think about here, one person who is network friends with 5 other. So next, 7 people network friends with 4 others. The rest, I don't know how many rest people we have, the rest are friends with 3 other people in the network. So should we say the unknown rest of the number of people to be x? So we have 3x over here. This doesn't tell us the total degree of G yet because of the unknown variable x. However, if you read this sentence here, the network contains 48 pairs of network friends. 48 pairs of network friends, that means that we have a total number of 48 edges. Do you understand? That means the total degree 96. Now we can probably find out the x because we know the total degree of G, which is 96. I leave you to figure this algebra. X is equal to 15. What does it mean, everyone? 15 people are network friends with 3 other people. So those people are the rest. Those people were the unknown from the question. How many people are in the network now? Well, we know 15 from this category 4. And we know 7 from category 3, 1 from category 2, and 3 from category 1. So 3 plus 1 plus 7 is 11. 11 plus 15 is 26 people in the network. Okay, let's do one last thing for this section 10.1. All right, here's the last statement that we're going to prove in this section 10.1. The statement is, prove that in any graph there are an even number of vertices of odd degree. Let's just set up the situation. Do you know why I separated V's and U's like this? We only have 2 choices, either even or odd. Do you agree? So I split this vertex set into 2 different parts. Number 1 is V1 to Vn is the collection of vertices with odd degree. So let's call it this way. And let's call U1 to Um right here. Suppose we have m number of even degrees. Okay, everyone. Let's talk about even first. Let's add degrees of U1, U2 up to Um together, and let's call it that number is e. Let O be the degree, the total degree for the odd ones, degree of v1 plus up to degree of vn. Do you know what this t stands for? This t stands for the total degree of g. For example, this t must be equal to even this e number and o number together. So t is equal to e plus o. Do you agree? I have a good news. The total number of degrees in g is always even, right? So if I rearrange the terms, I get the following. Everyone, E is even, T is also even number. Even number subtracted by even number is what? Even number, do you agree? So the number O is even as well. Okay, let's not forget about writing that T is even by corollary 10.1.2. Please write this hint somewhere on your notes, and we're going to use this soon. In the meantime, let's finish off the proof. We already proved that the O is the difference of two even numbers. So this number O, which is a collection of degree of v1 plus degree of v2 plus degree of vn, this is even number. So far we have. Did you notice that we have a sum of n odd integers? Because did you notice that degree of v1 is odd, degree of v2 is odd, so we have a set of all the degree vertices here. So all of these numbers are odd integers, and hence sum of this is even hypothesis implies that the n, the number of terms n must be even. That's the end of the proof. Thank you very much.